Our second speaker is Jiaoyang Huang from Courant Institute, and he will talk about random matrix statistics. Sorry.
Just use this.
Yeah, it should be fine.
Yeah, I want to first thank the organizers for this great conference. So several years ago, when I was a student, I was taking an advanced quantum mechanics class in this room. And it's so great to be back here again at this great conference, which links quantum mechanics and mathematics. And the topic of my talk is on random matrix statistics. This is based on joint works with Amor. So for my talk, there will be three parts. So first, I will explain to you some of the background on random matrix theory, in particular, the Wigner matrices, which we know the eigenvalue statistics are universal. And next, I will show you some interacting particle systems, where we also see those random matrix statistics. And in the last part, I will tell you some of the ideas how to prove the convergence to the random matrix statistics. So let me first start with the background. So the Wigner matrices, the random matrices, were introduced by Wigner. He wanted to understand the energy spectra, the spectral gaps of heavy nuclei. And this picture is the experimental data for the energy spectra of heavy nuclei, the uranium. And Wigner wanted to understand the eigenvalue gaps, the gaps between two adjacent spikes. And we know those spikes, they are eigenvalues of the Hamiltonian of the system, but the Hamiltonian of a heavy atom, it's a pretty complicated object. At that time, 1950s, Wigner simply didn't have a supercomputer to solve it and get the locations of those eigenvalues. That's why he decided to use a random matrix. And his insight is like this: for the complicated quantum system, it's pretty chaotic. So the Hamiltonian probably statistically similar to a large random matrix. And those eigenvalues, they should be similar, at least statistically similar to the eigenvalues of a large random matrix, and which are pretty easy to compute. And the first model he uses is this Gaussian orthogonal ensemble, so which is an n by n, a real symmetric random matrix. And those entries up to the symmetry in the upper half triangle, they are independent normal random variables. They have a mean 0. And the diagonal entries, they have variance 2. Off diagonal entries, they have a variance 1. So the variances are chosen in this way so that the whole matrix is orthogonal invariant. If you conjugate it by an orthogonal matrix, the law does not change. That's why it's called the Gaussian orthogonal ensemble. If we further normalize every entry by 1 over square root n and compute its eigenvalues, you will get this perfect semicircle from -2 to 2. And Wigner wanted to understand the energy gaps, the gaps between two adjacent eigenvalues. Because it's an n by n matrix, there are n eigenvalues. So typical distance between two adjacent eigenvalues will be roughly 1 over n. So if we take out the two bulk eigenvalues, lambda I subtract lambda I plus 1, we need to normalize it by a factor n. Now this is an order 1 random variable. And now we know it converges to a distribution because it's a Gaussian meta distribution, first computed by Gaussian and meta. It turns out this matches pretty well with the experimental data. This zigzag curve, it's the energy gap for the histogram for heavy nuclei. And this curve, it's not the statistic fit. It's a theoretical prediction given by the Gaussian orthogonal ensemble. So they match pretty well. And for the Gaussian orthogonal ensemble, it's a random matrix with Gaussian entries. So it's natural to ask what will happen if we replace those Gaussian entries by other distributions. Does it still match with the experimental data? So that's why Wigner introduced a slightly larger family of random matrices. Now we call them Wigner matrices. And it's an n by n matrix similar to the GOE. It's either real symmetric or complex Hermitian. And those entries in the upper half triangle are independent, but they are not necessarily Gaussian. Together with another physicist Dyson and mathematician Meta, they formulated this bulk universality conjecture. So they conjecture those bulk eigenvalue statistics, like the gaps between two adjacent eigenvalues. They should only depend on the symmetry of the matrix, like either it's real symmetric or complex Hermitian. It should be independent of the details of the model, like the law of those individual entries. So in other words, you just take any large n by n matrix, fill in with any distribution you want, like the Bernoulli distribution, which takes value 0 and 1, each with half probability, as long as you normalize it to have a mean 0 and a variance 1 over n. Then you compute the eigenvalue gaps, you will always get that Gaussian distribution. A half century after they formulate this bulk universality conjecture, it was finally proven by Tao and Wu under the 4-moment matching. They assume the entries' first 4 moments match with the Gaussian distribution. And the more general result was proven by Shen and Yao using Green's function and Dyson's Brownian motion. So this is about the bulk eigenvalue statistics. It turns out those extreme eigenvalue statistics, like the law of the largest or smallest eigenvalue, they are also of great interest. And if you remember for the Gaussian orthogonal ensemble, it's formed the semicircle. The largest eigenvalue roughly concentrates around 2. So if you take it out, lambda 1, subtract 2, and then you need to normalize by n to the 2/3. That's because of the square root behavior at the edge. And this guy is of the order 1, converged to the Tracy-Wiedemann distribution beta equals 1, first discovered by Tracy and Wiedemann. And similarly, if you consider a complex Gaussian matrix, each entry has a complex Gaussian, also mentioned in Freeman's talk, then do the same scaling, you will get the Tracy-Wiedemann distribution for beta equals 2. And this picture is a Tracy-Wiedemann distribution for beta equals 1. If you look at it, it's really close to a Gaussian distribution. But because it's defined in this way, this distribution is not centered. The mode is not at 0. It's biased towards the negative axis. Also, those two tails, they are not symmetric. It might be hard to see it from this picture, but the left tail, it goes to 0 much faster, behave like e to the minus x cube. And the right tail, it goes to 0 slightly slower, behave like e to the minus x to 1.5. And similar to the bulk universality, it was also proven for those Wigner matrices. Essentially, as long as those entries, they have a bounded force moment, then you take out the largest eigenvalue, you always get this Tracy-Wiedemann distribution. So for Wigner matrices, those eigenvalue statistics, it's well known and proven to be quite universal, independent of the law of individual entries. And this provides the test case for the insight of Wigner. And it's natural to consider more general families of random matrices. Like for Wigner matrices, it's pretty dense. You can also consider sparse random matrices from sparse systems. Like if you look at the adjacency matrix of those sparse graphs, it's also known as long as the average degree of each vertex grows with the size of a graph. Or in other words, for matrix, as long as the non-zero entries in each row and column grows with the size of the matrix, you always get those random matrix statistics. And another is the Wigner matrices, it has independent entries. One can also consider matrices with correlated entries, or entries have a spatial correlation. As long as the correlation decays sufficiently fast, we will still get those Tracy-Wiedemann distribution or Gaussian distribution. And what's more is, it turns out those random matrix statistics, they also appear in many other settings way beyond those matrix setting. So as written by Freeman Dyson, for any complex system, if it has many strongly correlated components, then we expect to see those random matrix statistics. And next, I will mainly focus on those Tracy-Wiedemann distribution. And now we know those Tracy-Wiedemann distribution, it's just a building block of a bigger picture. It's a marginal distribution of a process called the Airy-2 process. Okay, so the easiest way to introduce the Airy process is from this Dyson's Brownian motion. Freeman Dyson, he took a dynamical approach to the random matrix theory. He considered this matrix valued Brownian motion. It's an n by n matrix. If beta equals 2, it's a complex Hermitian. Each entry, it's a complex Brownian motion. And for beta equals 1, it's a real symmetric. At each entry, it's a real Brownian motion. Then for this matrix Brownian motion, you can integrate out its eigenvectors. Then you will get the dynamic of its eigenvalues. Lambda I is the ith eigenvalue. So it's given by this stochastic differential equation. Now we call them Dyson's Brownian motion. It has the first stochastic term. It's Wi just the Brownian motions. It depends on the parameter beta. And the second drift term is singular. Because of this 1 over lambda I minus lambda j singularity. So those eigenvalues, they repel each other. So they will not collide. And for beta equals 2, there's another interpretation for those Dyson's Brownian motion. You can also obtain them by just consider n Brownian motions, starting from the eigenvalues of A0. And condition them to level intersecting, they do not cross each other. Then you get this Dyson's Brownian motion. So here is a simulation for Dyson's Brownian motion starting from 1 point, and they start from 2 points. Because those particles, they repel each other, so they will span bigger and bigger interval. So to make it slightly more stabilized, you can take the map which sends the infinite to 0. Then in this way, you will get this Brownian watermelon. So this is simply, you just start n Brownian motion from 0 at time t is minus n, and the condition them to come back to the origin when t equals n. Meanwhile, this stay along intersecting, they do not cross each other. Then you will get this picture which is similar to the pattern of a watermelon. If you take one slice of this Brownian watermelon, it's an n-particle system. It has the same law as the eigenvalues of the Gaussian unitary ensemble. And we know the top particle, the marginal distribution of the top line, it converges to the Tracy-Widom distribution. And what we know more is this T point, roughly it's at the location square root 2 times n. And the top path, it fluctuates vertically on the scale n to the 1/3 and horizontally on the scale n to the 2/3. So we can scale the time by n to the 2/3, space by n to the 1/3. Everything is of order 1. You will get some line ensemble. The fluctuation is of order 1. And also because of the boundary of the watermelon, it's curved like locally around this T point. It's look like a parabola facing downward. So to make it flat, we need to add a parabola to it. Then everything is flat. It turns out you will get after this n to the 1/3, n to the 2/3 scaling, you will get some stationary process, the top line, which is the Airy-2 process, first introduced by Professor Ashburn. And it's a stationary process. As a marginal distribution, it's given by the Tracy-Widom distribution. And if you look at this picture, we can just do the same n to the 1/3 and n to the 2/3 scaling for all those extreme paths. In this way, they will jointly converge to something we call the Airy line ensemble, introduced by Coleman and Hammond. And typically, if there are interacting particle system, particles repel each other, we will usually see the Airy-2 process from the scaling limits of the top path. And it turns out the Airy-2 process, it also appears laterally in many random growth models. Like in the biology lab, if you look at the growth of a bacteria colony, the boundary curve, it's believed to be given by the Airy-2 process. And this picture is the growth of liquid crystal obtained by those physicists in Japan. They just repeat it for many times and measure the rough boundary curve. And it turns out the fluctuation of the boundary curve, if you do it many times, that it matches pretty well with the Tracy-Widom distribution. And conjecturally, many of those random growth models, the interface can be characterized by the KPZ equation. And the Airy process is believed to govern various phenomena related to those KPZ equation. And in the past 10 years, there are a lot of progress in this direction. I will not elaborate. And the the next model I'll show you where we will see those array process is from those dimer models. So here it's some special dimer models are called the tiling model. Like the first picture, it's called the lozenge tiling model. It's simply just given some domain. You tile it with those three types of lozenges: the diamond, the green one, and the blue one, and also the red one. And you can view this also. This is also equivalent to the dimer model on the hexagonal lattice. Another way to think about the lozenge tiling is you can think it as a pile of unit boxes. Like this is just a pile of unit boxes. So if you think it in this way, it's naturally associated with some surface. Like this, if you only look at the green diamonds, this is level 1, level 2, level 3. So it gives some 3D surface. And sometimes because of this, it's also called the planar partition, because it's some lateral generalization of the integer partition. And on the right-hand side, it's the domino tiling. You simply tile the domain with either the horizontal or vertical dominoes. It's just a dimer model on the square lattice. And depending on the white and black boxes we cover, we can further divide the dominoes into those 4 types. And for random tiling model, like the random lozenge tiling, it's simply just the uniform probability measure on all possible tilings of a given domain. You just uniform randomly pick one. And here are some more simulations of those tiling models. So a key feature of those random tiling model is the existence of the frozen region. Like close to the color of those pictures, you will only see one type of the lozenge or one type of those dominoes. And also it has this liquid region close to the center. Around each point, you will see all 3 types of those lozenges. And it was proven for any general domain, if the mesh size goes to 0, then you will always have some limit shape characterized by some variational problem. And there's a boundary curve which separates the frozen and the liquid region. And it was also proven, at least for the polygonal domain, this boundary curve which separates the frozen and liquid region, if the mesh size goes to 0, it's always converged to some algebraic curve, which we call the limiting arctic boundary curve. And it's analytic, but possibly have some singularity like this cusp singularity. And we know this boundary curve, it has some limits. If you ask for the fluctuation of the boundary curve, again here we will get this area 2 process. And those models, they are uniform tiling models. One can consider some more complicated tiling models with some weights. Then you will get some more bizarre pictures. Like for this picture, you can think it's a pile of unit boxes. If you further weight it by Q to the volume, then you will get this triangle-shaped liquid region. Also, if you tie this trapezoid domain with some wedges removed from the trapezoid, you will get this heart-shaped liquid region. And for those pictures, they are the domino tiling with doubly periodic weights. So you have some weights along the vertical and the horizontal directions. Then you will get this new phase called the gas region. So it's not completely frozen, but the correlation decays much faster than the liquid region. Or you will get this quasi-frozen region. You have 2 types of those lozenges, they alternate. So, but although the pictures, they look quite different, but if you look at this boundary curve, which separates the frozen region and the liquid region, you will always get the area process. So because for all those very specific examples, specific domains, we always get the area process. So it was conjectured, at least for those random lozenge tiling. So it's conjectured for arbitrary polygonal domain. If the mesh size goes to 0, along those boundary, we will always get the area 2 process. And in the joint work with Armour, we give a proof for this conjecture for generic polygonal domains. And more precisely, we prove things like you can just look at the limiting Arctic boundary curve, just any point, which is not a cusp point, and it's not a tangent point, where this limiting Arctic boundary is tangent, it's tangent to the boundary of the polygonal domain, where we expect to see something different. And then you just take any other points, zoom in, just by the n to the 1/3 at the n to the 2/3 scaling. Then the top pass, it always converges to the area 2 process. And we prove something slightly stronger. If you ignore those frozen lozenges, like the green one, and the red and yellow lozenges, they will form paths from the left to the right. And jointly, those extreme paths, they converge to the area line ensemble. And here the generic, we mean we do not allow some specific singularities on the Arctic boundary. Like we do not allow the technodes where the liquid region separates into two and they are tangent to each other on the technode. And also we do not allow those cuspidal turning points, which are those cusp points where the tangent at the cusp point is parallel to the sides of the polygon. And for like polygons with generic side lengths, like this 12 gun, we can just tune its side lengths. So we can show generically it satisfies our condition. So those extreme paths, they always converge to the area 2 process. So you can view this as some kind of edge universality for Lorentz tiling. Just for arbitrary polygonal domain, you will almost always get the area 2 process. Okay, so in the last part, I will just quickly explain to you some of the idea for the proof. So like, as I mentioned, those tiling models, they are just some special cases of the dimer model. So for dimer model, it's a determinantal point process because the partition function for the dimer models on any bipartite planar graph is given by the determinant of the casting matrix. So those random tiling models, they are also determinantal point process. And because of this, the correlation function, you can find some type A Lorentz at a place and type B Lorentz at another place. Those correlation functions are explicitly given by the minors of the inverse of the casting matrix. However, for those models, the casting matrix is a giant matrix. It's n squared times n squared matrix, which is typically pretty hard to invert. For those specific domains, the Aztec diamond, hexagonal domains, they can in fact explicitly invert the casting matrix and write down the kernel, do some asymptotic analysis, then you will get the area kernel, which characterizes the area process. But for general domains, the obvious challenge is we simply do not know how to analyze the inverse of the casting matrix. And for our proof, we just take another approach. Instead of directly show the converge to area process, we just do some comparison. We just locally compare our model, general model with some exact solvable model, and then conclude, and if we can see they are close to each other, then we can conclude the convergence to the area process. And we divided our proof into those 3 steps. So anything can be divided into 3 steps. But here, really, those 3 steps, they require different techniques. Like for the first step, we just first show some concentration estimates. Like for those tiling models, if you ignore one type of those lozenges, like the green lozenge, the red and yellow lozenge, they will form paths from the left to the right. So you can interpret this as a Markov process. And we can actually approximate the generator of the Markov process and analyze this Markov process. And in this way, we can show those paths, actually they concentrate around some deterministic paths. In particularly the top path, it will concentrate around this Arctic boundary. And we can show bound the fluctuation by n to the 1/3 plus some epsilon. Epsilon can be arbitrarily small. This is essentially optimal because we expect the correct fluctuation for the boundary curve is n to the 1/3. And once we have it, next step, we need to find some model we can compare with. So in this case, we will simply use this hexagon, which was known, those extreme paths converge to the Airy line ensemble. And in the last step, we will locally compare those extreme paths from the general domain with the extreme paths from the hexagon. And to do it, we will need to use some property of the random tiling model, because here we consider the uniform tiling model. And we will have those domain Markov property. Just essentially, we just look at some small box. We can resample what's inside this box. So in terms of those line ensembles, it simply says, if we have the left boundary point, and also the right boundary point, and also the bottom boundary point, what's inside is simply given by the law of those non-intersecting Bernoulli walk from the left to the right, and they do not intersect at above the bottom curve. And another property we will use is this monotonicity, which just tells us if we have two of those Bernoulli line ensembles, if the boundary data one is above another one, like if those blue dots on the boundary is above this yellow dots, at the bottom path, the green one is above this yellow one, then we can actually couple these two Bernoulli line ensembles such that ice green curve is above ice yellow curve. So everything is above. Then by using this monotonicity, we can just cook up two hexagons. We can tune the side lengths of this hexagon very carefully to construct another two extreme line ensembles, such that one is slightly above the line ensemble from the general domain. One is slightly below the line ensemble of the general domain. And using the concentration estimate as an input, then we can just carefully construct this line ensembles from hexagon such that their difference is small, much smaller than n to the 1/3. Then after we scale everything by n to the 1/3, we can conclude they will go to the same limit. So all of them will go to the Airy line ensemble. So this is how we prove this edge universality based on this comparison. Okay, so let me just quickly summarize here. The random matrix statistics. So for the system, if there are a lot of independence, then we typically expect to see the bell curve, the Gaussian distribution or Poisson distribution. But for a system, if like a heavy atom, if it has many particles strongly interacting with each other, if you have many components which correlated strongly, then we expect to see those random matrix statistics like the Gaussian meta distribution or Tracy-Widom distribution. But the main challenge to prove those random matrix statistics is because the lack of characterization of those random matrix statistics. And we know they come from the Gaussian matrix, and we have explicit formula for the density for the probability, like they are given by some complicated Fredholm determinant. But that's all we know about those random matrix statistics. And for our proof of the edge universality for Lorentz tiling, and also for those proof for the universality for the Wigner matrices, more or less we all use the idea of the comparison. Like we first prove some kind of concentration estimate, like the concentration, the largest eigenvalue concentrates around 2, or the top pass concentrates around the Arctic boundary. As the second step, we just find some exact solvable models we can compare with. Like in the Wigner matrix setting, we use the Gaussian orthogonal ensemble or Gaussian unitary ensemble to compare. For the tiling model, we will use the tiling of the hexagonal domain to compare. As the last step, we just show, oh, those models, they are close to each other, at least locally. Then we will get the local statistics converges to the random matrix statistics. And there are many, thanks to this three-step strategy, in the past 10 years, a lot of those exact models are discovered. Now we in fact have a zoo of those exact solvable models. We also have several ways to do those kind of robust comparison. So thanks to this three-step strategy, things are reduced to this concentration estimate. but it can still be very challenging because it's really model specific. But at least now we know to prove the Tracy Wiedemann distribution, the key is to get this n to the 1/3 scaling limit. There are many other models we expect to see those random matrix statistics. I hope in the future this approach can be used to prove them. I want to thank you for listening.
Thank you, George. I want to remind everybody, wait for the microphone, and also please say your name.
Okay, thank you for a beautiful talk. My name is Eddie Fari. I wanted to ask you something. If you look at the Sheraton-Kirkpatrick model, do you know what that is?
Oh, not
No.
really. Can you explain?
Okay, well, anyway, the reason I'm bringing it up is because this is a meeting where physicists talk to mathematicians. The Sheraton-Kirkpatrick model is a spin model where the couplings are given exactly by that Gaussian ensemble.
Oh, this is a spin class.
Yeah, the spin glass
Ah,
model.
yes.
Okay, that's what Parisi won the Nobel Prize
Yeah.
this year for analyzing the ground state of it. So I was asking you whether there are any connections between the kind of random matrix stuff you do and the analysis of Parisi and others to find the ground state of a spin model, which has exactly those Gaussian couplings.
Yeah, actually, for those spin class, the spins like for SK model, it's a discrete, which takes value 1 at -1.
Doesn't matter.
Oh,
It-
if you also consider the spherical spin class, actually a lot of techniques from random matrix can be used to prove the fluctuation for the ground states, the energy of the ground states at the universality for that ground states. They also I think for the original proof of the Paris's formula, they use some kind of interpolation between the model with the Gaussian model. And here, actually, a lot of ideas from random matrix, like the interpolation between general Wigner matrices and the Gaussian matrix, also use the same idea. Like the first proof for the universality, which by Tao and Wu, which require the first 4 moments of the entries to match with the Gaussian distribution. What they did is they just sequentially replace each entry by a Gaussian. And if you can control and see those local eigenvalue statistic does not change if you just sequentially replace each entry, then you can prove the universality. I think this idea was also used in the SK model.
Thank you.
I was wondering whether, oh, sorry, this is Michael Friedman. I was wondering whether your models, some of them are conformally invariant.
Oh, yeah, actually for those tiny model, it's conjectured to be conformal invariant. And if you look at the liquid region, look at the fluctuation of the liquid region, it converges to some Gaussian free fields with a 0 boundary condition. And it has some complex structure, which is given by the variational problem, which characterize the limit shape.
Is the Schramm-Livner equation relevant to your work here or not?
Oh, there's some more delicate conjecture about the geometry of the dimer model where we expect to see those SLE.
Hi, here is Li Yuan, and I have a question regarding the boundary condition when you are doing the tiling model. Because I think that you have those symmetries, so actually you can always rotate the picture, but did you set some specific boundary condition for those vertex or the angle to fix the color to get those configuration?
Oh, so you mean the tiling model?
Yeah.
Typically, the tiling model, you can think it as some 3D surface. Usually when we give some domain, you will also need to specify the height on the boundary. So that, yeah, you need to specify the domain and also the height, and then you can discuss how to randomly sample one of those height function.
Okay, so I have no more questions. I thank the speaker again.
Thank you.